So, yes, Sharma, that side.
Yes, sir. Good afternoon, sir.
Good afternoon. So, yes, Sharma, you have applied for the, I can say, data science into research and development part.
Right, sir.
Okay, fine. So, Sharma, could you please introduce yourself?
Sure, sir. So I am currently a BTech graduate and I have been a web developer. I have created several web development projects. Plus, after my graduation, I shifted my domain from web development to machine learning and data science specifically. So when it
Is
comes,
there any reason for that?
it was like in what we do in web development is, yeah, okay, we code something and it appears on that. And that's a thing. I have learned it and I have learned it up to a limit. Then afterwards, I want to change my domain because these cutting edge technologies are like super impressive. Why not to do stuff like why not to try hands on this? Because we should try and we should find out what is our forte. So that's why I changed my domain and let's see how it goes. And it's going pretty well till now. Okay, so in data science also, I took the means part which interests me because I was very fascinated by self-driving cars and all these autonomous robots, how they do stuff. So I choose a
So, you know that this profile is for research part
right, sir.
in reinforcement learning.
Right, sir. Yeah, right,
Okay, fine. So let's start some basic uh, topics about reinforcement learning. Okay.
right, sir.
So Sharma, could you just tell me that how would you explain reinforcement learning to a kid?
Okay, sir. Okay. When we have to do explain to a kid. Okay. We can take an example of either of chocolates or marks. Okay, let's do of marks because when we are kid, because we are very conscious about our marks. So we can I can start it with marks. So, okay. So I'll ask a kid, okay, so today I'm gonna teach you a reinforcement learning and in a simpler way, obviously, because how a kid will understand that. So I'll ask him, okay, so what if you score 100 out of 100 marks? How you will feel? And you will be rewarded by your parents or teachers, right? So you'll feel happy, right? You'll feel joyous. Great. But what if you score 0 marks or less marks, like let's say 10 out of 100? So what will be the scenario? Like you will feel sad and you might get scolded. So that's a penalty for you, right? So like this, I'll fix him, means I'll pull off this reinforcement learning topic. Okay. Now listen, what we are doing in reinforcement learning is we are teaching our robot. Robot is our agent. We are teaching our robot to do trial and error, and learn to score full 100 marks, right? So that's we are doing, and how we are teaching it using by the help of computers and mathematics, right? So this is how I'll make him or her understand that this is reinforcement learning. That involves reward, penalty. If you get reward, you will keep doing that thing, and if you get penalty, you will improve yourself and will choose another path to do, and then the maximize the reward. That's the basic thing.
Okay, fine. That is pretty cool. Um, let's say we have ML, right?
Right.
And in ML, we have supervised learning algorithms,
Mm-hmm.
unsupervised learning algorithms,
Right.
and there is third one also semi-supervised.
Right.
So how this, I can say, reinforcement learning is different from these learning?
Okay, sir. Shall I write it down?
Yeah, sure, you can.
Okay, sir. So when it comes to reinforcement learning in general, so in supervised, we have labeled data, right? So we have labeled data. In unsupervised, we don't have labeled data, right? We don't have the true output of it. We use unsupervised for clustering and all those things. So we have unlabeled data, we can say unlabeled data. And in semi-supervised, we have half a labeled data and half a unlabeled data, right? That is semi-supervised. Okay. So at some point of time, we have labeled data also, and at some part of semi-supervised learning works with unlabeled data. When it comes to reinforcement learning, we have no data. We don't have any data. We have an environment, an agent, and mathematics with us. So we have an agent and we have some environment, and environment is basically those things only, means the environment or the surroundings which this agent has to work into, right? So this robot has to work into. So in RL, we don't have any data. So we use some algorithms like Q learning algorithm we have, and there are a lot of algorithms, and we try to solve the MTP because that's also a thing. So we use Q learning, plus we have exploration and exploitation, which is basically what we are doing. We are trying stuff and then fixing our errors and then reaching a certain point which we want to maximize it, right? So there is a final goal we have in our mind, and an agent which knows nothing about the environment and has no knowledge, no data, basically. So it's like teaching a kid how to do some stuff. So it's like that.
Okay, fine. That would be cool. But you know that in RL, okay, we have an agent and critic model. You
Yes,
know
sir.
about that,
Yes, sir.
right? Okay. But in GAN, we have a generator and a discriminator,
Right, sir.
right?
Mm-hmm.
So how are they different?
Okay.
Can you give me some points?
Yes, sir. Okay, so I have studied GAN also, and how much I know about GAN. In GAN, what happens? We have a generator and a discriminator, and there is an adversarial nature between them. Means one want to fool another, right? So we want a discriminator to have 0.5 accuracy, which means that the images which will be generated, or images or data being specific, not just images, data being specific generated by the GAN, we want this generated data to be distinguished from the real data, and we want to fail this discriminator and makes its accuracy 0.5, and which symbolizes that, because we have two choices only, either it is real or either it is fake, right? So that we want to do. So GAN is about diverging. GAN is about diverging. We can't control the process of GAN, right? We can't control the process of GAN. Like, it can make anything, because GAN is about imagination, what generator is making, and how much the discriminator is making that loss, right? Having the accuracy. So it is divergent. We can't control the output of the GAN, right? Obviously, we can make the GAN images or generated data closer to the real, but that's not specific. Means we don't know where where it will put the pixel, right? So we don't know that. Whereas in agent critic model, in reinforcement learning, critic has to, it is a convergent task, we can say. It's a convergent task. We have to converge at a specific point, which is the final goal. This agent will not gonna stop, and this critic will not gonna stop until and unless this specific final state has been reached. So it will keep on telling him, okay, you are making an error, you have to reach there. Don't take this part, take that part, right? So that's how it will be.
Okay, so give me some real world examples of reinforcement learning.
Okay, sir. Real-time examples. As I told you, I was very fascinated by self-driving cars. So self-driving car is an application of reinforcement learning in real world. Then we have air flight simulations and all kind of simulations. Then there was this popular movie which came out, The Free Guy, if you have heard of it. So in that also we have an AI inside a game, and that's basically an non-playable, they can say non-playable player or something, which they call him. So that's the thing. That's the power of AI. You can make him take decisions. So that's what it is about. Reinforcement learning is about taking decision by making mistakes. So
okay, so have you done any project which you think it is a damn cool project?
yes, sir. So this love for self-driving cars has been very crazy for me. So I took it for in a small version. I took this car racing version O from gym environment, which is of OpenAI, and inside that it is provided by Box2D. So there are some environments which has been provided by OpenAI, which is a subsidiary of Google only. So I imported this environment, and what was in this? There was this track, and I need to make this car to follow this track and go on this track, and there are some divergence, right? So there is some drift, or we can say turns.
So can
Right?
we convert this, I can say a software based car, okay, it is a software based car, into an hardware based car where we have a track, okay, and there is one car which is to be run on that track, which is made to be run on that track. So can we make this?
Okay, sir. That's means a bigger application of it, and that will require, because this was very small, and in this I was using PID controllers, which
No,
are
I'm saying that suppose, let's say, Just wait. Suppose let's say it is a track, right?
Right, sir.
And I want my car to be move on this track.
Right, sir.
So in I can say on software basis, you can do it
Yeah, in
with the help of
simulation we
RL.
can do it. Right.
But I want it in the hardware basis. Means these machines would be there, a real track would be there, and you want to make that move. Is it very
Right.
fascinating, right?
Yes, sir. It will be really fascinating. But here's the thing: when we work in simulations, and this is very small kind of simulation. Obviously, we can apply it on tracks, and that's what Tesla is doing basically. Right? I don't know what tech they are using and what algorithms they might be using, because that they can't disclose due to their security purposes. But there was this phenomena which I worked on to make this in software only, because hardware will require a mechanical team and then this research team also, and they will put together this work, how much drift, how much torque to apply. So that's a quite big thing about. But what I used for this software thing only was PID controllers, just to make this car stay on the center of this track. If it will diverge from it, so there was this function, this PID function only, PID controllers, which will make it to stay on the center of the road or track.
Okay, so the example which was I talking about was an example of IoT. You know about IoT, Internet of Things.
Right, sir.
So I can say that would be a part of IoT. Can you believe that?
Okay, it will be, obviously IoT is about Internet of Things and making it, because yeah, I think self-driving cars uses also signals also, like how much distance this side one car has to be with me. So they throw out
So
signals.
can I say that? Can I say that this IoT part is nothing but an advanced version of RL?
Okay. I have not much knowledge about IoT, but I can say with the help of reinforcement learning, because obviously that will be involved. If it's an AI inside a car, then certainly it will be reinforcement learning, because we don't have any data like these many data of these many roads. So it is not supervised and unsupervised. We can't take our car just to on trial and just do that. So obviously there had to be many trials before this real time thing. So yeah, it can be a future aspect, or future aspect, I can say a bigger aspect of reinforcement learning itself.
Okay, so there are two parts.
Mm-hmm.
One is exploration.
Right.
Okay, these are the two terms.
Mm-hmm.
And other one is exploitation. So what is the difference between these two?
Okay, sir. This is the main crux of this reinforcement learning. What we used to do in other machine learning algorithms or other deep learning algorithms, what we used to do, we had the data and we had to work on it. We have to think about the mathematics, like how to achieve this thing. But here we don't have anything. As I told you already, we have this agent. This is my agent, you can say. And this is my whole environment. This whole grid thing is my environment. Let's suppose for now it's a maze or something, any game, right? So exploration is about that it will try this path. This is my end goal, where it will get the maximum reward. So it will try it can try this path, it can try this path, it can try this path. So this trying of paths, trying and finding, that is involved in exploration. Trying and finding all the aspects which can be used to maximize the reward comes under the exploration part. And when it comes to exploitation is the part where we start taking the rewards, because once I found out that this path is giving me the maximum reward, so I'll start exploiting on that only. So I'll start exploiting this path only if I find that this is giving me the maximum reward. So that's about exploitation, going towards or taking out the rewards, taking out final steps basically.
Okay, so which among exploration and exploitation should be maximum and why it is?
Okay,
If I
sir.
can say that.
When it comes to exploitation, we just can't be just biased toward exploration or exploitation, because as you must have known, in data structures, we have this space-time trade-off, right? So we need to manage the space also, plus we need to take care of the time complexity also. So in here also, we have exploration and exploitation. We need to maintain both of them. We need to find, and there are several algorithms, which is epsilon greedy algorithms and There were several other algorithms which are upper bound algorithm also, to find out how much exploration to do for this specific task and how much exploitation to do for this specific task. So we need to manage, we need to balance both of them, because if it is just exploration, it's like knowledge. Exploration is like knowledge. If I am a human being, I'm just consuming knowledge, and I'm not using it somewhere. Usage of knowledge or implementation of knowledge is exploitation, and attaining knowledge is exploration. So if I'll just attain the knowledge and won't implement it, that will not be of any use. And if I don't learn something and I'll just go on the implementation part, that is also not good. So these must be balanced.
Okay, so that is pretty cool. So have you heard about Bellman equation?
Yes, sir.
So can you explain it?
Sure, sir. So in Bellman equation, before that, these are some terms like agent, as I already told, and environment. And then we have this is called policy. Then we have states, right? And then we have a reward and actions. So these are the terms which are there in reinforcement learning, and these will help me to take out the Bellman equation or explain the Bellman equation more nicely. So action is something which my agent can take in order to maximize its reward. Policy is the logic which I'm using to attain my final state or maximize the reward. State are the stages, you can say, or you can say the pieces. Like if I take chess game, if I take chess game as my environment, then the boxes, white and black boxes, are my states, right? And the pieces are my agents. And action can be different. Like for this bishop, the action will be different. For queen, the action will be different. It can move here, it can move here. So actions are those things. Reward is what? Reward is beating the king in this case. And environment is our chessboard, agent is our pieces. So this was about all the things in that reinforcement learning. But when it comes to Bellman equation, what Bellman equation help us in doing is this thing. Bellman equation would be like, the whole thing about it to find the value function. And why we need to find the value function? Because for a certain state, we are finding that, okay, now I'm in this certain state, whether it is good or not to be in this state. So that we need to find it earlier only. That we need to find whether my agent to be in this state will maximize its chances to maximize the reward or not. So Bellman equation helps in that thing. So Bellman equation is
it would be, first of all, suppose there are two blocks and first one agent is here. So will it be are you saying that before going to second block, it will see whether is it good to be in the second block, or after it has placed, then it will see?
Right, sir. That only what Bellman equation specifies. So I'll write the equation and then it would be more clearer. So shall I?
Okay, fine.
Okay, sir. So we are finding the value at a specific state. So this is value function at a specific state. What state that value holds? So we are applying that. So Bellman equation give us a value at that state, which as you told is what will be the chances being in that state, right? So this will be there, and this is equals to maximum by doing certain action, maximizing the reward plus this and this and this. So this is our Bellman equation, and this thing here is the future thing. As you told, like we have two boxes, and this agent will see whether to be in this state, it will be good or bad. So it will do it in future or it will do before moving, right? So that's the thing. The value of this state, first of all, the state which it is in right now, it will measure of that, because it's a recursive thing, because these are the future probabilities. These are the future probabilities.
So this would be dependable on another equation.
Right. This will be dependable on what? If it is s, and if it is st plus 1 for another time, right? So if it is st plus 1, and if we will go and find out st plus 1, that would be equal to maximum of a and the instantaneous reward at that state and action. This is our discounting factor. and this will be st plus 2. Now it will be there on, it will be dependent on the next month, like what it will take.
So how we are calculating this future part?
Right, sir. Right. So that's the thing. That's where this thing comes up, which is we call as MDP is the stochasticity. We are just means applying the probability of that stage, because we have one thing in our hand. In reinforcement learning, we have just one thing: maximize the reward. Maximize the reward. You do trial and error. So we do try and error and find out what are those values at that specific state. When for the next time the agent will traverse that path, it will already have the values which it has attained. So these values will be there by exploring. Now it have explored these paths, so these values will be there. These futures values will be there to find the actual state of that actual value of that state. So that's how this agent gonna take that out.
Okay, okay. Yeah, that would be cool. So in RL, there is a special difference, which we call as temporal difference.
Right, sir.
So can you specify that?
Right, sir. Okay, so when it comes to temporal difference, I should take an example like, okay, we have cleaning robots at our home. So if I can go with that example. So this is my small cleaning robot, whatever it is. Okay, this is my room. My room doesn't have lines, but just to make this specific here. So this is my room, and here is my dust, right? So its task is to remove this dust, right? So this is my cleaning robot. So this is what it has to do. But in a real world, we don't have these ideal conditions, right? Because if my fan is on, this dust will move here, or it will have this thing. Right, so this has been moved till here. So now what will be the change? So that what tells about temporal difference. Temporal difference, TD, is equals to Q. I am specifying as the value function only. It is the estimated value. So estimated new minus estimated old. Estimated value of that particular state where our end goal is, because now state has changed, because this was the older destination, or we can say final state which this robot has to attain, but now the scenario has changed. My fan was on and the dust moved here, right? So this is a different state. So if we subtract this from this, then we will find out the temporal difference. And
can you write the formula for it?
Right, I can say. So when it comes to temporal difference, we have the Q which we already know, and it is helpful in Q learning also. The temporal difference thing is helpful in Q learning also, which is an algorithm which we use to find the best policy for a reinforcement learning. So TD will be equals to, again, maximum value by doing certain actions and having instantaneous reward for that state, which will be S comma A, plus we have this discounting factor, then this QT plus 1. This was our only value function, which I told in Bellman equation. So this is my Q new is here, and I'll subtract Q old from this, the Q old part. So if it is T plus 1, and then it will be QT. So yeah, this is the temporal difference.
The new one minus the subtracted one. Okay.
Yeah.
Okay. That would be cool, and I can say that would make an end to your interview. And if you are getting selected, you will be getting a call from one of our HR for your personal interview. Right. Okay. And thank you for joining. You may leave up.
Okay, thank you so much, sir. Have a nice day.
Any questions for me?
Sure, sir. Like, if you can tell me, like, how should, like, as you have given the example of IoT, so like to usage of reinforcement learning in a real world scenario, obviously we'll be needing the hardware. So how these things gonna be?
It's I can say it's basically let me draw it. See this IoT. Okay. And with the help of we have so much of things. We have Arduino. Right. We have Raspberry Pi. Okay. We have Jetson Nano. we have these types of machines which are capable enough to do this type of work. Actually, I have seen one project where one student have developed this thing. It has a track like this, a circular track.
Right.
And I don't know about the machine name, whether it is Arduino or something. Uh, it was installed in one of the, I can say that it has 4 wheels, and it was trained just like that, that it should move on only this track, and it was colored with white. So I don't know about the backwards part, but I seems to have that this Arduino was trained to move on only white color part.
Okay, that's a line following robot, which we are talking about, right?
Yeah, correct, yes, because it is following that color only.
Right, sir.
So that was very fascinating. In terms of, I can say, self-driving cars, these types of algorithms will has to be processed now.
Yeah,
Okay,
definitely. So
I can
these,
say
yeah.
that
Mhm.
if my Tesla, for example, if my self-driving cars is trained in India,
Right.
will it be working in USA as well?
No, that they have different road types and scenarios, traffic. So there are very external
Right,
forces which made it.
right. So we want to make a type of self-driving cars which are helpful in India as well as in USA.
Right.
It's not to be the country dependent.
It's need to
Okay.
scale overall world, right?
Yeah, we need to scale and we need to train it more and more in harder places, like suppose in mountainous areas
Mhm.
or seed sites, just like that.
Right, sir.
Okay.
Mhm.
Yeah. Anything else?
No, no. Thank you so much, sir. He was such being nice to me. Thank you so much.
Okay. Thank you. Thank you. Ja.
Next second. Now.